This conference will
questions
now
are
be
there.
recorded.
So we have been learning many formulas and many theories on ray optics chapter. So today what we'll do, we'll solve few numerical problems and then our concept will be more clear. So the last part in this chapter is the instrument part, microscope, telescope. So among telescope, astronomical and terrestrial telescopes are there. So that topic we'll take in the next class. Today, whatever we have learned, actually we have covered the most important portions of this chapter, like all the lenses, mirror and prism part we have already discussed. So we'll take up questions based on those formula or theory we have already discussed. Okay. So the first question is, a disc is placed on the surface of a pond which has refractive index 5/3. A source of light is kept 4 meters below the center of the disc. What should be the minimum radius of the disc so that no light comes out of the source? See, this kind of question I had already discussed. So this is based on total internal reflection. If you remember, internal reflection. Okay. In short, it is called TIR, total internal reflection. And this is the concept of, see, we need the concept of angle of critical angle of incidence. Critical angle of incidence. Angle of incidence. Okay. So if you can try by yourself, that will be better. But there is a time constant, so we'll just discuss this. So see, the problem is, see, in pictorially, if I want to describe that, see, there is a source of light. See, first of all, the question is, suppose a disc. A disc is placed on the surface of pond. Suppose this is, say, this is certain like pond on top of the water surface. This is the surface of the water on the pond. Okay, in the pond. This is the water surface. Okay. On top of that, we are just keeping on opaque. So this is opaque. Opaque in the sense light cannot pass through that. So this is a disc. Okay, opaque disc. This is an opaque disc. This opaque disc we have kept on the top of the water surface, and at the below of the center of this disc, a source of light has been placed. Look, this is the source of light. This one. And this is opaque disc. This one. The question is, what should be the minimum radius of the disc so that you cannot see any light coming out from this source? Okay. since the water is a transparent medium, if you keep a source of light inside the water, you should be able to see some light coming out from that source. But we have kept an opaque disk on the top of the surface of the water, and just below the center of that, 4 meters below the center of that disk, this source has been kept. So at which condition this light will not go to your eye. The concept is angle of critical incidence or critical angle of incidence. So the light is actually, so this is air, this is water, pond water. Okay, so pond water has refractive index mu 5/3. Okay. Now that means the air is actually traveling from denser to rarer medium. Denser to rarer medium. Okay. Rare medium. So when light travels from denser medium to rare medium, then only there will be a particular angle of incidence. Particular angle of incidence. Look, this is actually that particular angle of incidence when, see, what is happening, light is getting refracted at the interface of air and water. So at this interface, when light comes from this source, see, since there is a disk over here, whatever light goes in between these two extreme rays, in between two rays, whatever light goes, it will be actually obstructed by this opaque. Okay, whatever light rays you take this way, in between these two extreme rays, all the light rays will be obstructed. So that is fine. But light must be going, see, from here and here, light should go, right? Light should pass through the air. Okay, it should pass through the air. But it will not go. At what condition? Condition is that if this, see, exactly at this edge of this disk, the angle of incidence, this angle, see, this is the angle of incidence. If this angle of incidence becomes the critical angle, as I have shown you here, if this becomes critical angle of incidence, then what will happen? At the critical angle of incidence, at critical angle of at theta c, that means critical angle of incidence, what happens during refraction? See, I'll write this is N2, suppose N2 sine theta c is equal to, suppose this has N1 refractive index, so N1 sine R, this is the Snell's law I should have written. So in this case, look, this R will be perpendicular. Look, this will be perpendicular. The ray will be, see, at the critical angle, ray will be grazing the interface, It will be on the interface, it will not go to this medium, okay? The second medium. In fact, the angle of refraction will be 90 degrees. Okay, angle of incidence will be 90 degrees and light go through the surface both ways. As you can see from here also. I'll clean maybe everything. See, look, at an angle of critical incidence, the light is actually passing on the or lying on the surface of the water, but it is not going to the air. Okay, it is not going to the air. Okay, even see, this is a critical angle. Critical angle. Now, if the angle of incidence is more, suppose I take another ray like this. So what will happen to that? That will directly go to the water itself, because after that, see, any angle of incidence greater than critical angle of critical angle, any angle of incidence greater than critical angle, TIR happens. That means total internal reflection will happen. So the light will not go at all to the other medium, air. It will just come back to the water itself. So this is the concept. Now we'll try to find out what would be the minimum radius of this disk such that this particular thing happen. That means at least the extreme rays which are at the edge, which are actually getting incident or is incident. See, these two rays they are incident at the edge of this disk. At least if they are at the critical angle of incidence, then no light will go to the first medium, second medium. Okay. All right. So this condition, what we can write, we know already. Suppose this is mu and this refractive index mu is equal to 1. So I can take 1. Okay. So at critical angle of incidence, at critical angle of incidence, mu is equal to 1 by sine theta c. So this is the formula you should remember at critical angle of incidence. Okay, I have got this. Very nice. Now look, I can take this triangle. See this angle theta c means this also will be, these are opposite angle. So let us take this, suppose O, suppose this is S, and suppose this is R. So triangle OSR. This is a right angle triangle if you look here. Okay. So OS you know already, this is 4 meter below this disk. So 4 meter you know. So from this triangle I can write what is tan theta. Let us write tan theta c. Okay. Let us write tan theta c. What is tan theta c? So this is hypotenuse, this is the base, and this is perpendicular. So OR, which is nothing but the radius of the disk divided by the height is h. Okay. Okay, I'll write it here. So we'll write tan theta c. This will be equal to r by h. Okay. This is OR, that means radius of the disk itself, and h is the height of the, like, depth of the source from the surface. Now look, this I can write. So I have to find out what? I have to find out R. Let us write this. This is tan theta c. Okay. So look, I have got what is sin theta c. So I can make use of that. So this is sin theta c divided by cos theta c. So what is sin theta c? That is 1 by mu. So h by mu. And cos theta c will be divided by cos theta c. This will be 1 minus sin theta c square. That means 1 over mu square. 1 over mu square. So if we just do a little bit of simplification over there, what we get is this one from here. Sorry, R. R is equal to h. Then there was mu over here, and here will be another mu, and this will be mu square minus 1. Okay. So this will give you the answer. Let us see what it is. So mu goes off. then h will be 4 meter. Mu was given 5 by 3. So 5 by 3 means this will, see, 3 will come over here, and this is 5. 5 by 3 means 25 minus 9. So here will be again, this will be 25 minus 9. 16 means you will get 4. So look, this is 4 into 3 divided by 4. 4 goes up. So the answer will be 3 meter. Okay, 3 meters should be the radius. Okay, Deepa, is this clear? Is this clear to you? So look, if you don't do this much, at least you should remember. If you don't want to do this much, at least you should remember the final formula for this kind of problem. What is the formula? The radius. Formula for the radius will be h over under root mu square minus 1. So this is the formula. You should remember. What is the mu? Mu is the refractive index of the liquid or water, whatever. So this is the formula you should remember. Okay. Directly you can use this 4, and mu means mu is given 5 by 3. So look, what will be the R? So this is 4 meter. Here mu is 5 by 3 square minus 1. So this will give you 3 meter. Just look here. So 3 denominator will go here, and 25 minus 9. This will give you again under root 16. This part 16 under root 16 means that will be 4. So finally you'll get that. Okay. So anyway, I'm not doing this again. You just use this formula and try to do it. Okay. I'll just move on to the next problem. So this problem you have to read carefully. Any problem you want to solve, you have to read it and understand the problem itself first. So a plano-convex lens is made of material having refractive index 1.6. So refractive index of the medium or the material by with which the convex lens, plano-convex lens is made, that is 1.6. Mu is given. So the radius of curvature of the curved surface, radius of curvature of the curved surface is given. So what will be then the focal length of the lens? See, they have asked you plano-convex lens. So what do we mean by plano-convex? I have taught you plano-convex. Convex. See, plano-convex means there will be one convex surface and another will be plane. This can be this way or maybe this way also. Kind of that. So this is actually plano-convex lens. So one side is one surface. See, we know the original lens, spherical lens is this. Okay, this is spherical lens. One side is this way, this is radius. So this is actually having two spherical surfaces for normal lenses. Okay, two spherical surfaces are there. When there will be plano-convex or plano-concave, even in concave also, normal concave, there are two spherical surfaces. Okay, but when we talk about plano-concave, then it will be like this. Okay, plano-concave or like this. Okay, plano-concave. So one surface will be plane and other surface will be concave. Okay, so here the question is related to plano-convex. So I'll just remove the plano-convex part. I have figure for you. Look, the question is planar convex lens, and this lens is made of a material having refractive index 1.6. Radius of curvature of the curved surface is given. So what is the radius of this plane surface? So what is the radius of curvature of the plane surface? So this will be actually infinity. You have to remember that whenever you see any plane surface that has radius of curvature infinity. That's why plane mirror has focal length infinite, since it has infinite radius of curvature, right? So you have to use this fact that plane surface has infinite radius of curvature, and the curved surface has like radius of the curved surface is given 60 centimeter. Now you have to find out what is the focal length. So which formula you want to use for this? Do you know which formula are you going to use here? Do you remember something? We have learned two formulas related to length, which will relate the object distance, image distance, object distance, and focal length. Okay, this is where we get this relationship between these three. Length is equation, thin length is equation. Okay, length is equation. So that is different. So that will be 1 by p minus 1 by u is equal to 1 by f. But here there is no refractive index and no radius of curvature. That means this formula we cannot use. So then we have to remember which formula is relating radius of curvature, refractive indices, etc. with the focal length. So there is only one formula related to that. So that is, see, this one. What is this? This is called actually length maker's formula. Length maker's formula. So this length maker's formula you have to remember 1 by f over mu2 minus mu1 divided by mu1 whole into 1 by r1 minus 1 by r2. I'll just explain what is this equation. See, mu2 is always refractive index of the material of the lens. Material of lens. And what is mu1? Mu1 is the medium in which the lens is kept. In which the lens is kept. If nothing special is mentioned, then we have to think that the lens is kept at the air. Okay? So if it is kept in vacuum or air, then mu1, the refractive index of the medium will be 1. Okay? We can take this. If suppose it is mentioned that the lens is dipped into water, then this mu1 will be refractive index of water 4 by 3. Okay, or 1.33. This will be obviously given. Sometimes it will be mentioned that a planar convex lens is, or a convex lens is dipped into water, oil. So in that case, the refractive index of the oil will be a mu1, not mu2. Mu2 is the refractive index of the material of the lens, like the material of which this lens is made. Okay, you have to remember this. You should not forget and should not do the mistake. Okay, so now in this case, a planar convex lens is made of material having refractive index 1.6. That means this is mu2, 1.6. If the radius of curvature of the curved surface, that means radius of curvature of this surface is given. Suppose this is a R1. R1. This is 60 centimeter given here. Okay. Then what is the focal length of the lens? This plano-convex lens. Okay, I'll just wrap this portion to get some space. Look, I'll just make use of this place for the solution. Look here, I have to write this is the lens maker's formula in general. This is a general formula. This is general formula. Okay, I have to use this for my problem. So in this problem, mu1 is 1. Okay, so mu2 is 1.6. R1 is what and R2 is what? So R2, let us say this R2 is a radius of curvature related to plane surface. So plane surface it is infinity, and R1 for the curved surface 60 centimeter it is already given. Okay. Now you use here, you write down this formula for your problem here, given here. I'll just remove this part. So we have to write the lens maker's formula for the given problem. We'll write that. We have got the information. Now we'll write that formula. Look here, 1 by f is equal to mu2 is 1.6, mu1 is 1 divided by 1. Then 1 by R1 is 1 by 60 centimeter. Okay, that is in centimeter. And what is 1 by R2? 1 by infinity. This will give you 0. Okay, this will give you 0. 1 by infinity means 0. So finally, what you get, this is 0.6 over 60. Okay, this one into this part. Okay, so if you do little bit of calculations over here, so you'll get 6 by 600. So you'll get 1 over 100. Okay, so this is reciprocal of the focal length. Then what is the focal length? F will be 100 centimeter. Okay, centimeter inverse. Okay, so do you get my point here? How I solve this problem? This was a plano-convex lens. If you are given plano-concave, similar way you can do that. And also I had already mentioned one more problem. Let me see whether I have that problem. So when you have dipped a lens in some liquid, then you have to write this lens maker's formula with proper mu2, mu1, R1 and R2. Okay, so that's how you have to solve. So this, in this case, the correct answer is this one, D. In the previous case, the correct answer was C. Okay. Okay, so we'll just go to the next question. So this is another question. Suppose two identical plano-convex lenses, okay, each having radius of curvature of the curved surface 20 centimeter. That means, okay, let me read the whole problem. Are placed with their central portion in contact. The intervening space is filled with material of refractive index 1.7. What is the focal length of the combination? I'll show you the figure. See, what is the question? Question is actually, there are two identical plano-convex lenses. I have taken two identical plano-convex lenses like this. Okay, this is one, another one I have to take. So they are actually, okay, plano-convex glass lenses. Glass lenses means mu2 is given, that is 1.5. Glass lens means glass and refractive index 1.5. Okay, and these are identical means they are refracted both this mu2 and mu1. Okay, let me read this again. And the radius of curvature of the curved surface of the planar convex lenses are given. Since they are identical, both are having 20 centimeter radius of curvature of the curved surface. Now, how we are keeping this? We are keeping this in contact. There are two planar convex lenses. So we'll keep their central portion in contact and keep like this. And see, this part is intervening region. In between them, this part will be empty or intervening region. This intervening region, if we fill with something, some liquid having refractive index 1.7, then what will be the focal length of the combination? See, I hope I have, I could make you understand the problem. The problem is there are two planar convex lenses. See, this one, and this is another one. Okay, with this white shade. See, look, there are two planar convex lenses. They are kept in such a way that only the central portion is touching somewhat. Okay, like this. Then the intervening region, these portions are intervening region. Okay, that you fill with water, or here the liquid which is filling this intervening region is having refractive index 1.7. So this is the case now. So finally, what is happening? By doing this, what is happening? You can look from here. So this mu1 and mu2 both are made of glass. So this mu1 and mu2 is equal to mu g is equal to 1.5 refractive index. If required, then we can use that. And what is mu3? Mu3 is given as 1.7. This is the refractive index of the liquid with which the intervening region of the lens combination has been filled with. Look then what happens, from the figure you can very well understand. See, this is planar convex lens. The combination is now, this is planar convex lens. This will act as planar convex lens. This intervening part with refractive index this will act as another lens, but this lens is, see, the concave lens. It is actually a concave lens. It will act as concave lens. Okay, and again I have the second plano convex lens. Okay, so finally what is happening? By doing this, just by keeping the plano convex lens in contact with the center part alone, and if you fill with the water the intervening part, then you will in fact have three lenses. Two are plano convex lenses, and the intervening region with filled liquid of refractive index 1.3 will be another lens that will be acting as concave lens. Now, if you want to calculate the focal length of the combination, you know how to do that. Because if you have more than two or at least two lenses which are kept in combination together, so the focal length 1 by f will be 1 by f1 plus 1 by f2 plus 1 by f3, like that it goes. Okay, so then you have to find out what are the focal lengths, individual focal lengths of planar convex, this planar convex and this concave. And then if you add like this, you will be able to find out the focal length of the combination. Do you understand, Deepa, the concept? Deepa, do you understand the concept? Can you respond to me, or you can write in the message box also, chat box. So these are very important. These are the problems which are being asked in various competitive exams. Okay, this type of problem will come in that competitive exams. Okay, so that's why I have taken numerical problems class today. Okay, if you don't understand, you can stop me any time. So this is the concept that this length will act as, this combination will act as combination of three different lenses to our plano-convex, and the third is concave lens simply. Okay, we'll just remove this, you can see from the figure itself, and then I'll be using this portion. So here also you look, we will be using the length makers formula for, suppose I want to write for convex. So what you write, see in the previous, see in this case, if you have this length alone, then you have mu2 as mu g minus 1 divided by 1. Okay, and into whole into 1 by r1. Okay, 1 by r1, and over 1 by infinity, because plane surface has refractiveness infinity. Sorry, focal length infinity. Now you get what? Mu g minus 1 divided by r1. Okay. In fact, both the equivalent length has same radius of curvature. So mu g minus 1 by r for 1. Okay. 1 planar convex length. For 2, you'll get multiplied 2. So you got this focal length of the planar convex lens. Now you have to find out focal length of the concave part. So in this concave part, you have two surfaces. There is no plane surface. So two surfaces, you have to write all the way. So see, in this case, you have to do one thing. See, this is mu liquid minus 1 divided by again 1. Okay, but I think this is not true, because what you have to do, you have to write mu2 by mu1, mu2 by mu2 minus mu1 by mu1. So in this case, look, this is the liquid, and this both sides, what is there? There are glasses. So it is actually inside the glasses you can think of. So that's how you have to do here. Mu2 minus mu1. Mu1 is mu g divided by g. So into 1 by r1 minus 1 by r2. You have to write this. Okay, the whole formula. Since this is r and r both are same r, and one among them will be with the minus sign. Okay, one will be there with a minus sign, because one surface is this way having radius of curvature, another one is this way. So R2, let us say R2 is positive, R1 is negative. So in this way you will get a negative sign in the beginning, and so this will be R and R. So 2R you will get 2 into mu2 minus mu g over mu g. Okay, into R, like this. So if you solve this like this, this is mu g. Okay, let us do the numerical part here. This portion. Okay, I'll just do it. Okay, let me write this 1 by f here clearly. 1 by focal length, so this will be 2 into mu g minus 1 over r. Okay, R is 20 centimeter. All right, we'll use that. And this portion I'll just remove. So I have got for that. Okay, now I have got for concave. For concave also I'll write it here. What we get with minus sign 2 mu 2 minus mu g divided by mu into g into r. Okay. Now look here and do the calculation. What is mu g and mu? Okay, this is according to my figure. This is mu 3. Mu 3. Now we have to add the reciprocal of the wavelength. Sorry, focal length. F1 plus F convex 1 over F concave. Okay, there are two convex, so we have got 2 into mu g minus 1 over r, and here it will be plus. Okay, so anyway there is a minus sign, so we can just write it minus 2 into mu 3 minus mu g over mu g into r. Okay, so if you put the values, mu g is 1.5, so 1.5 minus 1 divided by, this is 20 centimeter, and in this case also 2 into mu 3, so you'll get actually 1.5, sorry, 1.77 minus 1.5, so you'll get 0.2 over mu g again down, and this is mu g is 1.5 into r over here. So if you just do this r also 20 centimeter. If you do this, you must be getting this value. Okay, minus 50 centimeter. Okay, so please try to do the problem. I have already discussed. You have to just find out the final value. Okay, and see how you get that. What is the value you get? Okay, so I'll take the next question. If the refractive index of the material of an equilateral prism, now I will be discussing about the refraction at the refracting surface of a prism, triangular prism. So here the prism shape is equilateral triangle, and refractive index of the material like with which the prism is made is given. Then what is the minimum angle of deviation? Look, I have to find out first what are the available formula for the minimum deviation of prism, and that too will relate the refractive index. I have this formula, delta minimum is equal to mu minus 1 into A. A is the angle of refraction, sorry, angle of refracting angle of the prism or angle of prism. So this is the angle of prism. So since it is equilateral triangle, okay, just suppose this is a equilateral triangle, so angle of prism will be 60 degrees. So this is okay. Now you have to find out what is angle of deviation. But this formula is valid only for small angle. Okay, when A will be very small, or delta also will be very small. Small angle of prism. When A will be small angle, that time this formula is valid. Otherwise, there is another formula which relates the refractive index, minimum deviation, minimum angle of deviation, and this angle of prism. What is that? This is mu is equal to sine delta minimum, okay, plus a over 2 divided by sine a by 2. Okay, so this is the another formula. Look here, refractive index is given. So since small angle is not mentioned, so we will not be using this formula. We'll be using instead this formula. Okay, since small angle, that's the word is missing in this problem. So I'll just clean this part. We cannot use this for small angle. So look here, mu is given root 3. The same thing I'm writing on the right hand side. Sine delta m we don't know, plus a by whole divided by 2 divided by a by 2 sine over. Look here, since it is equilateral triangle, then I can write a is 60. Look here, I can write this 60 over 2. And this also will be sine 60 over 2. Okay, look, this sine 60 over 2, that means in the denominator, this will give you half. Okay, so this I have to find out what is delta minimum. The question is minimum angle of deviation you have to find out. So this, see, sine 60 degree by 2 means it is sine 30 degree. Sine 30 means half. Half means here it is in the denominator, so half will actually be multiplied like this. So this will give you sine delta plus. Okay, this is delta minimum. All right, so now what you can do, we can just write this also in terms of sine 60 degree. Okay, then this sine 60 degree will be equal to this sine of delta m okay. So now from both sides, if we compare both sides of this equation, we can write that 60 degree is equal to, okay, I think I have done a small mistake over here somewhere, a plus delta by 2. Okay, anyway, oh, there was 2 over here, yes. So this delta m plus 60 degree divided by 2 is equal to this. So delta m will be actually 60 degree. So this is how you can find out what is minimum angle of deviation for the given information for the given prism. If you know the refractive index, if you know the angle of prism, then you can find out what is the minimum angle of deviation. Okay, Deepai, are these cognizable? Are you understanding this? Okay, so I think I'll take the last problem, this one. Okay, let's say read this problem. Suppose the angle of prism is A. So I have a prism, triangular prism. It is not mentioned whether it is isosceles, equilateral, or right angle triangle, but we will just take a simple triangle Okay, so angle of prism is given A. One of the refracting faces of the prism is silver. See, this is silver. Silver means then this surface will act as a reflector. It will act as a mirror. Will act as a mirror. If it is silver, this is silver. It is said that it is silver. Alright. If it is silver, fine. So now the question is that a ray of light incidents at an angle 2A angle of incidence. Where at this surface, if it is ABC, this AB surface will draw a perpendicular like this. So this will be angle of incidence, which is 2A angle. Okay, double of this angle of prism. Now the ray is coming. This is incident ray, and in fact this is I is equal to this 2A. So after refracting here, if the light is returned back through the same path, suffering reflection from the silver face. So it generally how it goes like here, and then it refracts or emerges from the prism in general. But in this case, since it is acting as a mirror, and see, after reflecting, the light will be actually retracing the path, or returning to that path itself. Okay, that means what? In a mirror, when light returns back in the same path, at what condition? At normal incidence. If this is a mirror, then light comes normally, it will go back like this. Okay, that means here there was a normal incidence at this surface. Okay, normal incidence means what will be the angle? So this is actually R1, angle of refraction. Generally, there will be another angle of refraction over here, R2. But since it is normal incidence over here, that's how light is getting reflected in the same path and retracing and coming out of the prism itself. So this R2 will be 0 for normal incidence. For reflection or refraction, normal incidence will give you 0 angle of incidence. Okay. So this is R2 is equal to 0. I hope I have shown you the this dispersion, like how it happens in the first figure itself, first problem itself. Now look, I know another formula for a prism. So here the question, let me finish. So return back in the same path. So we have read up to that, and then what is the refractive index of the material of the prism? I have to find out what is mu of this prism. So this is the full question. I'll repeat the question. Suppose there is a prism ABC, triangular prism, which has angle of angle of prism A, and one surface. Suppose this AC surface is silver, such that it will act as a mirror. So through the another surface, first surface, suppose AB, through that surface all light comes and gets into the prism. Okay, and angle of incidence at this AB is 2A. So you have to, so this 2A, and then after refraction it is actually hitting the AC and coming back in the same path. That means this is normal incidence, so R2 is equal to 0. And we know actually there is a relation between this refracting angle of refraction R1 plus R2 is equal to A angle of prism. This we know. Okay, this is the property of angle of prism. So if this is the case, see R2 is 0 here. So what is R1 then? R1 is this. That means we have got all the information See, we have got the information for refraction at this surface 1. Okay. So what we get? We get angle of incidence over here. Okay, we have got that, and we have got what is angle of refraction. Angle of refraction at the surface will be R1. So that R1 is here, angle of prism. You also angle of prism. Okay. So we'll just now let me remove this part, and okay, let me remove everything. So we are just applying Snell's law at this interface. Okay, this is 2A, angle of incidence. Okay, so this goes normally and then come back in the same path. So this is R1, this is R2 is 0. So we have got R1 is equal to A, and I1, angle of incidence, or I simply, that is here at this AB surface we have got. So I'll write Snell's law for this AB interface itself. So these are the information. So if I write Snell's law, what I have to write? So suppose refractive index of air, it is going from air to prism. So refractive index of air into sine of I is equal to, this is mu, suppose mu into sine R1. Okay, this is what we know. Then we have to find out what is refractive index. So sine I divided by sine R1. Look here, R1 is nothing but A and I is 2A. So what I have to write? Sine 2A divided by sine of angle A. Now what we have got, I'm writing here for further calculation. So sine 2A divided by sine A. Okay, this is what I have got. So if you just simplify a little bit using identity of trigonometry, sine 2 theta means 2 sine theta cos theta. So sine A cos A here. What? This is sine A again. So you just strike this out. So you will get mu is equal to 2 into cos of A. So this is the refractive index of the medium of the prism or material of the prism. Okay. So this is how you have to solve numerical problems from this chapter. Okay. So next day, that is on Sunday, I think 26th, will be learning the instruments, optical instruments, telescope, peripheral, and other telescope, microscope, their working principle, etc. will be learning. Okay, so I'll stop it here for today. So today's class was fully on numerical problems, basically on lenses, lens matters formula, and prism, dispersion by prism, sorry, refraction of prism, minimum angle of deviation, and various formulas related to that. Okay. All right. So Deepa, do you have any doubt, any question or query? Whatever so far we have discussed. Okay. So if you don't have any problem, any query, may I stop it here? Okay. Okay then. I'll stop it here.